welcome back to CS50. So this is the end of week 4. Just one announcement first. So the so-called fifth Monday is coming up this coming Monday. This is the opportunity to change from SAT on SAT to letter grade, or from letter grade to SAT on SAT. Annoyingly, that process does require a signature because you have to fill out one of those pink add drop forms, because technically the SAT on SAT version and the letter grade version have distinct catalog numbers. But no big deal. Do just come up to me or to Rob or to Lauren at any point, or email us if you don't have the kind of paperwork you need today. And we will be sure to help you take care of that before Monday. All right, so today, and actually, there's a bit of an echo. Can we tone me down a bit? OK. OK. So today we introduce a topic known as pointers. And I'll admit that this is one of the more complex topics that we tend to cover in this class, or really any introductory course that uses C. But take my word for it, particularly if your mind feels a bit more bent today and in the weeks to come. It's not representative of you getting any worse at this. It just means that it's a particularly sophisticated topic that I promise a few weeks hence will seem all too strikingly straightforward in retrospect. I still remember to this day I was sitting in Elliott Dining Hall, sitting next to my TF Nishat Mehta, who was a resident of Elliott House, and for some reason this topic just clicked, and which is to say that I too struggled with it for some amount of time, but I will do my best to help avoid any such struggle with a topic that ultimately is quite powerful. In fact, one of the topics we'll discuss in the weeks to come is that of security, and how you can actually exploit machines in ways that were not intended. And those exploitations are typically the result of bugs, mistakes that we people make by not understanding some of the underlying implementation details via which programs are made. Now, to make this seem all the more user-friendly, I thought I'd play a 10-second preview of a little claymation figure named Binky, who was brought to life by a friend of ours at Stanford, Professor Nick Parlanti. So allow me to give you this teaser of Binky here.
Hey, Binky, wake up. It's time for pointer fun.
What's that? Learn about pointers? Oh, goody!
That is Stanford computer science. So more on that to come. Sorry, Nick. So recall that last time we ended on this really exciting cliffhanger whereby this function just didn't work. At least intuitively, it felt like it should work, simply swapping the values of two integers. But recall that when we printed out the original values in main, 1 and 2, they were still 1 and 2, and not 2 and 1. So let me actually switch over to the appliance, and I wrote up a bit of skeletal code in advance here, where I claim that x will be 1, y will be 2. I then print out both of their values with printf. I then claim down here that we're going to swap them. I left a blank spot here for us to fill in today in just a moment. Then I'm going to claim that the two variables have been swapped. Then I'm going to print them out again. And so hopefully I should see 1, 2, 2, 1. That's the super simple goal right now. So how do we go about swapping two variables? Well, if I propose here that these cups might represent memory in a computer. This is a few bytes. This is another few bytes. Could we have a volunteer come on up and mix us some drinks? If familiar? Come on up. What's your name? Jess. Come on up, Jess. If you don't mind, we have to put the Google Glass on you so we can immortalize this. OK, Glass. Record a video. And OK, we are good to go with Jess here. All right? Nice to meet you. So what I'd like you to do here, if you could quite quickly, just pour us like half a glass of orange juice and half a glass of milk, representing effectively the numbers 1 in one cup and 2 in the other cup. This is going to be good footage. No, it's OK. Nice. All right, so we have 4 bytes worth of orange juice, or call it the value 1. Now another 4 bytes worth of milk, we'll call it value 2. So x and y respectively. All right, so now if the task at hand for you, Jess, in front of all of your classmates, is to swap the values of x and y, such that we want the orange juice in the other cup and the milk in this cup, how might you, before you actually do it, go about doing this? OK, wise decision. So you need a bit more memory. So let's allocate a temporary cup, if you will, and now proceed to swap x and y. Excellent. So very well done. Thank you so much, Jeff. And there you are. Little souvenir. Okay, so obviously a super simple idea, completely intuitive, that we need a bit more storage space in this form of cup if we actually want to swap these two variables. So let's do exactly that. Up here, in between where I claim I'm going to be doing some swapping, I'll go ahead and declare temp, and I'll set it equal to, say, x. Then I'm going to change the value of x, just like Jess did here with the milk and orange juice, to be equal to y. And now I'm going to change y to be equal to not x, because now we would kind of be stuck in a circle, but rather temp, where I temporarily, or where Jess temporarily put the orange juice before clobbering that cup with the milk. So let me go ahead now and make this. It's called noswap.c. And now let me run noswap. And indeed, I see, if I expand the window a little bit, that x is 1, y is 2, and then x is 2, y is 1. But recall that on Monday, we did things a little differently, whereby I instead implemented a helper function, if you will, that was actually void, called it swap. I gave it two parameters, and I called them A and I called them B. Frankly, I could call them X and Y. There's nothing stopping me from doing that, but I would argue it's then a little ambiguous, because recall from Monday that we claimed that these parameters were copies of the values passed in, so it just kind of messes with your mind, I think, if you use exactly the same variables. So I'll instead call them A and B, just for clarity, but we could call them most anything we want. And I'm going to copy and paste, effectively, this code from up there down into here, because I just saw that it works. So that's in pretty good shape, and I'll change my x to A, my x to A, my y to B, and my y to B. So in other words, exact same logic, exact same thing that Jess did. And then the one thing I have to do up here, of course, is now invoke this function, or call this function. So I will call this function with two inputs, x and y, and hit save. All right, so fundamentally the same thing. In fact, I've probably made the program unnecessarily complex by writing a function that is taking some 6 lines of code, whereas I previously had implemented this in just 3. So let me go ahead now and remake this, make no swap. All right, I screwed up here. This should be an error that you might see increasingly commonly as your programs get more complex, but there's an easy fix. Let me scroll back up here. And what's the first error I'm seeing? Implicit declaration. What does that typically indicate? Oh, I forgot the prototype. I forgot to teach the compiler that swap is going to exist, even though he doesn't exist at the very beginning of the program. So I'm just going to say, not int, void, swap, int A, int B, semicolon. So I'm not going to re-implement it, but now it matches what's down here. And notice the absence of a semicolon here, which is not necessary when implementing. So let me remake this, make no swap, much better shape, run no swap. And damn it, now we're back where we were on Monday, where the thing didn't swap. And what's the intuitive explanation for why this is the case? Yeah? Exactly. So A and B are copies of x and y. And in fact, any time you've been calling a function thus far that passes variables like ints, just as swap is expecting here, you guys have been passing in copies. Now, that means it takes a little bit of time, a split second, for the computer to copy the bits from one variable into the bits of another, but that's not such a big deal. But they're nonetheless a copy. And so now, in the context of swap, I am, in fact, successfully changing A and B. In fact, let's do a quick sanity check. Printf, A is %I, new line, and let's plug in A. Now let's do the same thing with B, and let's do the same thing here. And now let me copy those same lines again at the bottom of the function after my 3 lines of interesting code have executed, and print A and B yet again. So now let's remake this, make no swap. Let me make the terminal window a bit taller so that we can see more of it at once, and run no swap. X is 1, Y is 2, A is 1, B is 2, and then A is 2, B is 1. So it is working just like Jess did here inside of swap, but of course it's having no effect on the variables in main. So we saw a trick whereby we could fix this, right? When you're faced with this scoping issue, you could just punt and make X and Y what kind of variables instead? You can make them global, put them at the very top of the file, as we did even in the game of 15. We use a global variable. But in the context of the game of 15, it's kind of reasonable to have a global variable representing the board, because the entirety of 15.c is all about implementing that game. That's what the file exists to do. But in this case here, I'm calling a function swap. I want to swap 2 variables, and it should start to feel just sloppy if the solution to all of our problems when we run into scope issues is make it global, because very quickly our program is going to become quite a mess. And we did that very sparingly as a result in 15.c. But it turns out there's a better way altogether. Let me actually go back and delete the printfs just to simplify this code. And let me propose that this indeed is bad, but if I instead add in some asterisks and stars, I can instead turn this function into one that's actually operational. So let me go back here and saying asterisks is always difficult, so I'll say stars. All right, just fess up to that one. All right, and now what am I going to do instead? So first of all, I'm going to specify that instead of passing an int into the swap function, I'm instead going to say int star. Now, what does the star indicate? This is that notion of a pointer that Binky, the claymation character, was referring to a moment ago. So if we say int star, the meaning of this now is that A is not going to be passed in by its value. It's not going to be copied in. Rather, the address of A is going to be passed in. So recall that inside of your computer is a whole bunch of memory, otherwise known as RAM, and that RAM is just a whole bunch of bytes. So if your Mac or your PC has 2 gigabytes, you have 2 billion bytes of memory. Now let's just suppose that just to keep things nice and orderly, we assign an address, a number, to every byte of RAM in your computer. The very first byte of those 2 billion is byte number 0. The next one is byte number 1, number 2, all the way on up, to roughly 2 billion. So you can number all of the bytes of memory in your computer. So let's assume that that's what we mean by an address. So when I say int star A, what's going to be passed into swap now is the address of A. Not its value, but whatever its postal address is, so to speak. Its location in RAM. And similarly for B, I'm going to say the same thing, int star B. As an aside, technically the star could go in other locations, but we'll standardize on the star being right next to the data type. So swap signature now means give me the address of an int and call that address A, and give me another address of an int and call that address B. But now my code here has to change, because if I declare int temp, which is still of type int, but I store in it A, what kind of value? To be clear, am I putting in A with the code as written right now? I'm putting the location in A, but I don't care about the location now, right? Temp exists just as Jess's third cup existed for what purpose? To store a value, milk or orange juice, not to actually store the address of either of those things, which feels a little nonsensical in this real world context anyway. So really what I want to put in temp is not the address of A, but the contents of A. So if A is a number like 123, this is the 123rd byte of memory that A just happens to be occupying, that the value in A happens to be occupying. If I want to go to that address, I need to say star A. Similarly, if I want to change what's at the address A, I change this to star A. If I want to store in what's at the location A with what's at the location at B, star B, star. So in short, even if this isn't quite sinking in yet, and I wouldn't expect that it would so fast, realize that all I'm doing is prefixing these stars to my variables, saying don't grab the values, don't change the values, but rather go to those addresses and get the value. Go to that address and change the value there. So now let me scroll back up to the top just to fix this line here, to change the prototype to match. But I now need to do one other thing. Intuitively, if I've changed the types of arguments that swap is expecting, what else do I need to change in my code? When I call swap, because right now, what am I passing to swap still? The value x and the value of y, or the milk and the orange juice. But I don't want to do that. I instead want to pass in what? The location of x and the location of y. What are their postal addresses, so to speak? So to do that, there's an ampersand. Ampersand kind of sounds like address, so and ampersand, the address of x and the address of y. So it's deliberate that we use ampersands when calling the function, and stars when declaring and when implementing the function. And just think of ampersand as the address of operator, and star as the go there operator, or more properly, the dereference operator. So that's a whole lot of words just to say that now, hopefully, swap is going to be correct. Let me go ahead and make, let's actually rename the file, lest this program still be called no swap. I claim that we'll call it swap.c now. So make swap./swap. And now, indeed, x is 1, y is 2, and then x is 2, y is 1. Well, let's see if we can't do this a little bit differently as to what's going on here. First, let me zoom in on our drawing screen here. And let me propose for a moment, and whatever I draw here will be mirrored up there now. Let me propose that here's a whole bunch of memory, or RAM, inside of my computer. And this will be byte number, let's say, 1. This will be byte number 2. And I'll do a whole bunch more, and then a bunch of dot, dot, dots to indicate that there's 2 billion of these things. 4, 5, and so forth. So there are the first 5 bytes of my computer's memory. All right, very few out of 2 billion. But now I'm going to propose the following. I'm going to propose that X is going to store the number 1, and Y is going to store the number 2. And let me go ahead now and represent these values as follows. Let's do this as follows. Give me just 1 second. 1 second. OK. I want to make this a little, let's do this again. Otherwise, I'm going to end up using the same numbers unintentionally multiple times. So just so we have different numbers to talk about, let's call this byte number 123, 124, 125, 126, and dot, dot, dot. And let me claim now that I'm going to put the value 1 here and the value 2 here, otherwise known as X and Y. So it just so happens that this is X, this is Y, and just by some random chance, the computer, the operating system, happened to put X at location number 123, and Y ended up at location 124. Damn it, I should have fixed this. Oh, man. Do I really want to do this? Yes, I want to fix this and be proper about this today. Sorry, new at this. 127, 131, and I didn't want it to be this complex, but why did I change the numbers there? Because I want the ints to actually be 4 bytes. So let's be super anal about this, so that if 1 happens to be at address 123, the 2 is going to be at address 127, because it's just 4 bytes away. That's all. And we'll forget about all of the other addresses in the world. So X is at location 123, Y is at location 127, and now what do I actually want to do? When I call swap now, what's actually going on? Well, when I call swap, I'm passing in the address of X and the address of Y. So for instance, if these 2 pieces of paper now represent the 2 arguments, A and B, to swap, what am I going to write on the first of these, which I'm going to refer to as A? Exactly, 123. So this I claim is A. This is the parameter A. I'm putting the address of X in there. What's that? What's that? No, that's OK. Still good. Still good. So this is A. And now on the second piece of paper, this is going to be B. And what am I going to be writing on this piece of paper? 127. So the only thing that's changed since our previous telling of this story is rather than pass in literally 1 and 2, I'm going to pass in 123 and 127. And I'm now going to put these inside of this box. All right, so that black box now represents the swap function. Meanwhile, let's now have someone implement the swap function. Would someone up here like to? All right, come on up. What's your name? Charlie. All right, Charlie, come on up. So Charlie is going to play the role of our black box. And Charlie, what I'd like you to do now is implement swap in such a way that given those 2 addresses, you are actually going to change the values. And I'll whisper in your ear how to run the TV here. So go ahead, and you're the black box. Reach in there. What values do you see for A, and what values do you see for B? OK, exactly. Now pause there for just a moment. The first thing you're going to do now, according to the code, which I'll now pull up on the screen, is going to be to allocate a little bit of memory called temp. So I'm going to go ahead and give you that memory. So this is going to be a third variable that you have accessible to you called temp. And what are you going to write on the temp piece of paper? OK, well, not necessarily pointer. So the line of code that I've highlighted on the right-hand side, let's start there, says star A. So A is currently storing the number 123. And just intuitively, what did star 123 mean? But specifically, if A is 123, star A means what? The value of A, or no, more casually, go there. So let me propose that holding the A in your hand, go ahead and treat that as though it's a map, and walk yourself over to the computer's memory and find us what is at location 123. Exactly. So we see at location 123 is what, obviously? OK, so what value now are you going to put into temp? Exactly. So go ahead and do that and write on the number 1 on the piece of paper that's currently titled temp. And now the next step that you're going to implement is going to be what? Well, on the right-hand side of the next line of code is star B. B, of course, stores an address. That address is 127. Star B means what, casually speaking? Yeah, go to that location. So go ahead and find us what's at location 127. Okay, of course, at location 127 is still the value 2. So what are you going to now store at whatever's at the location in A? So star A means go to the location A. What is the location A? Exactly. So now if you want to change what's at that location, I'll go ahead and run the eraser here and now put it back on the brush. What number are you going to write in that blank box now? Exactly. So this line of code, to be clear, let me pause what Charlie's doing and point out here. What he's just done is write into that box at location 123 the value that was previously at B. And so we've now implemented, indeed, this second line of code. Now, unfortunately, there's still one line remaining. Now, what is in temp, literally? Okay, it's obviously the number 1. That's not an address. It's just a number, sort of a variable from week 1. And now when you say star B, that means go to the address B, which is, of course, here. So once you get there, I'll go ahead and erase what's actually there. And what are you going to write now at location 127? Temp, which is 1. And what happens to temp in the end? Well, we don't really know. We don't really care. Anytime we've implemented a function thus far, any local variables you have are indeed local, and they just sort of disappear. They're reclaimed by the operating system eventually. So the fact that temp still has the value 1 is sort of fundamentally uninteresting to us. All right, a round of applause if we could for Charlie. Very well done. Sure. All right. So what more does this mean we can do? So it turns out that we've been telling a few white lies for quite some time. Indeed, it turns out that a string, all of this time, is not really a sequence of characters per se. It kind of is that intuitively, but technically speaking, string is a data type that we declared inside of the CS50 library to simplify the world for the first few weeks of class. What a string really is the address of a character somewhere in RAM. A string is really a number, like 123 or 127, that happens to demarcate where a string begins in your computer's memory, but it doesn't represent the string per se itself. And we can see this as follows. Let me go ahead and open up some code that's among today's source code examples. And I'm going to go ahead and open up, let's say, compare0.c. This is a buggy program that is going to be implemented as follows. First, I'm going to say something. Then I'm going to go ahead and get a string from the user in that next line. Then I'm going to say it again. Then I'm going to get another string from the user. And notice I'm storing one of these strings in a variable called s and another of these strings in a variable called t. And now I'm going to claim very reasonably that if s equals t, the strings are the same, you type the same thing, else the strings are not the same thing. After all, if we inputted 2 ints, 2 chars, 2 floats, 2 doubles, any of the data types we've talked about thus far, to compare them, recall we made very clear a while ago that you don't do this, because a single equal sign is, of course, the assignment operator, so that would be a bug. We use the equal sign, which indeed compares things for true equality. But I claim this is buggy. If I go ahead and make compare 0, and then do /compare0, and I type in, let's say, hello, and then let's say hello again, literally the same thing, the computer claims I typed different things. Now, maybe I just mistyped something. I'll type my name this time. I mean, hello. It's different every single time. Well, why is that? What's really going on underneath the hood? Well, what's really going on underneath the hood is the string that I typed in that first time, for instance, is the word hello, of course. But if we represent this underneath the hood, recall that a string is an array. And we said as much in the past. So if I draw that array like this, I'm going to represent something quite similar to what we did a moment ago. And there's actually something special here, too. What did we determine was at the end of every string? Yeah, this \0, which is just a way of representing literally 0, 0, 0, 0, 0, 0, 0, 0, 8 0 bits in a row. I don't know, frankly, what's after this. That's just a bunch more RAM inside of my computer. But this is an array. We've talked about arrays before, and we typically talk about arrays as being location 0, then 1, then 2. But that's just for convenience, and that's entirely relative. When you're actually getting memory from the computer, it's, of course, any of 2 billion some odd bytes, potentially. So really, underneath the hood, all this time, yes, this might very well be bracket 0. But if you dig even deeper underneath the hood, that's really address number 123. This is address 124. This is address 125. And I didn't screw up this time. These are now 1 byte apart. For what reason? How big is a char? A char is just 1 byte. An int is typically 4 bytes, so that's why I made it 123, 127, 131, and so forth. Now I can keep the math simpler and just do +1, and this is now what's really going on underneath the hood. So when you declare something like this, string s, this is actually, it turns out, char star. Star, of course, means address, aka pointer, so it's the address of something. What is the address of? Well, I'm the only one who can see the very important point I'm making, or think I'm making. So string, the sad thing is I have a monitor right there where I could have seen that. All right, so string s is what I declared previously, but it turns out, thanks to a little magic in the CS50 library, all this time, string has literally been char star. The star, again, means pointer or an address. The fact that it's flanking the word char means it's the address of a character. So if getString is called, and I type in HELLO, propose now, what has getString literally been returning all of this time, even though we've rather oversimplified the world? What does getString actually return as its return value? 123 in this case, for instance. We've previously said that getString simply returns a string, a sequence of characters, but that's a bit of a white lie. The way getString really works underneath the hood is it gets a string from the user, it plops the characters that he or she types in memory, it puts a \0 at the end of those sequence of characters, but then what does getString literally return? It literally returns the address of the very first byte in the RAM that it used for that string. And it turns out that just by returning a single address of the first character in the string, that is sufficient for finding the entirety of the string. In other words, getString does not have to return 123 and 124 and 125. It doesn't have to give me a long list of all of the bytes that my string is using, because 1, they're all back to back, and 2, based on the first address, I can figure out where the string ends. How? The special null character, the \0 at the end. So in other words, if you pass around inside of variables the address of a char, and you assume that at the end of any string, any sequence of characters as we humans think of strings, if you assume that at the end of any such string there's a \0, you're golden, because you can always find the end of a string. Now, what's really then going on in this program? Why is this program, compare0.c, buggy? What is actually being compared? Yeah. Exactly. It's comparing the locations of the string. So if the user has typed in hello once, as I did, memory might end up looking like this. If the user then types in hello again, but by calling getString again, C is not particularly clever, unless you teach it to be clever by writing code. C, and computers more generally, if you type in the word hello again, you know what you're going to get? You're just going to get a second array of memory that, yes, happens to be storing H, E, L, L, O, and so forth. It's going to look the same to us humans, but this address might not be 123. It might just so happen that the operating system has some available space, for instance, at location, let's say something arbitrary like this is location 200, and this is location 201, and this is location 202. We have no idea where that's going to be in memory. But what this means is that what is going to be stored ultimately in S? The number 123. What's going to be stored in T in this arbitrary example? The number 200, and all that means then is obviously 123 does not equal 200, and so this if condition never evaluates to true, because getString is using different chunks of memory each time. Now we can see this again in another example. Let me go ahead and open up copy0.c. I claim that this example is going to try but fail to copy two strings as follows. I'm going to say something to the user. I'm then going to get a string and call it s. And now I'm doing this check here. We mentioned this a while back, but when might getString return null, another special character, a special symbol, let's say? If it's out of memory, for instance, if the user's really being difficult and types an atrocious number of characters at the keyboard and hits enter, if that number of characters just can't fit in RAM for whatever crazy reason, well, getString might very well return null. Or if your program itself is doing a lot of other things and there's just not enough memory for getString to succeed, it might end up returning null. But let's be more precise as to what this is. What is s's data type really? Char star. So it turns out now we can peel back the layer of null. Turns out null is, yes, obviously a special symbol, but what is it really? Really, null is just a symbol that we humans use to represent 0 as well. So the authors of C and computers more generally decided years ago that, you know what, why don't we ensure that no user data is ever, ever, ever stored at byte 0. In fact, even in my arbitrary example before, I didn't start numbering the bytes at 0. I started at 1 because I knew that people in the world have decided to reserve the 0th byte in anyone's RAM as something special. The reason being, anytime you want to signal that something has gone wrong with regard to addresses, you return null, otherwise known as 0. And because you know that there's no legit data at address 0, clearly that means an error. And that's why we, by convention, check for null and return something like 1 in those cases. So if we scroll down now, this is just then some error checking. Just in case something went wrong, let's bail altogether and quit the program by returning early. This line now could be rewritten as this, which means what? On the left-hand side, give me another pointer to a character and call it t. What am I storing inside of t based on this one line of code? I'm storing a location, specifically the location that was in S. So if the user has typed in hello, and that first hello happened to end up here, then the number 123 is going to come back from getString and be stored, as we said earlier, in S. When I now declare another pointer to a char and call it t, what number is literally going to end up in t according to this story? So 123. So technically now, both S and t are pointing to the exact same chunks of memory. So notice what I'm going to do now to prove that this program is buggy. First, I'm going to claim with the printf, capitalizing the copy of the string. Then I'm going to do a little error checking. I'm going to make sure, let's make sure that the string t is at least greater than 0 in length. So there's some character there to actually capitalize. And then you might recall this from previous examples. ToUpper, which is in the ctype.h file, t bracket 0, gives me the 0th character of the string t, and ToUpper of that same value, of course, converts it to uppercase. So intuitively, this highlighted line of code is capitalizing the first letter in t. But it's not capitalizing, intuitively, the first letter in S. But if you're sort of thinking ahead, what am I about to see when I run this program and print out both the original S and the so-called copy t? They're actually going to be the same. And why are they going to be the same? They're both pointing to exactly the same thing. So let's do this. Make copy 0. It compiles OK. Let me run copy 0. Let me type something like hello in all lowercase, then hit enter. And it claims that both the original S and the copy are indeed identical. So what really happened here? Let me redraw this picture just to tell the story in a slightly different way. What's really going on underneath the hood when I declare something like char star s, or string s, I am getting a pointer, which happens to be 4 bytes in the CS50 appliance and in a lot of computers. And I'm going to call this s. And this currently has some unknown value. When you declare a variable, unless you yourself put a value there, who knows what's there? It could be some random sequence of bits from the previous execution. So when I, in my line of code, do getString, and then store the return value in S, getString somehow, and we'll eventually peel back how getString works, somehow allocates an array that probably looks a bit like this, HELLO \0. Let's suppose that this is address 123, just for consistency. So getString returns in the highlighted line there. It returns the number we said, 123. So what really goes inside of S here? Well, what really goes inside of S is 123. But frankly, I'm getting a little confused by all of these addresses, all of these arbitrary numbers, 123, 124, 127. So let's actually simplify the world a little bit. When we talk about pointers, frankly, to us humans, who the heck cares where things are in memory? That's completely arbitrary. It's going to depend on how much RAM the user has. It's going to depend on when in the day you run the program, perhaps, and what input the user gives you. This is just, we're dwelling on unimportant details, so let's abstract away and say that when you run a line of code like this, char star s gets the return value of getString. Why don't we instead just draw what we keep calling a pointer as though it's pointing at something? So I claim now that s up there is a pointer. Underneath the hood, it's an address, but it's just pointing to the first byte in the string that's been returned. If I now return to the code here, what's going on at this line? Well, in this highlighted line now, I'm declaring apparently another variable called t, but it's also a pointer. So I'm going to draw it as, in theory, the exact same size box, and I'm going to call it t. And now if we go back to the code again, when I store s inside of t, what am I technically putting inside of t? Well, technically, this was the number 123. So really, I should be writing the number 123 there. But let's take it higher level. T, if it's just a pointer, intuitively is just that. That's all that's being stored in there. So now, in the last interesting lines of code, when I actually go about capitalizing the 0th character in t, what is going on? Well, t bracket 0 is now pointing to what character, presumably? It's pointing to h, because t bracket 0, recall this is old syntax. T bracket 0 just means if t is a string, t bracket 0 means get me the 0th character in that string. So what that really means is go to this array, and yes, this might be 123, this might be 124, but it's all relative, remember. Whenever talking about an array, we have the advantage of talking about relative indices. And so now we can just assume that t bracket 0 is h. So if I call toUpper on it, what that's really doing is capitalizing the lowercase h to uppercase h. But of course, what is s? It's pointing to the same darn string. So this is all that's been happening in this code so far. So what's then the implication? How do we fix these two problems? How do we compare two actual strings? Well, intuitively, how would you go about comparing two strings for true equality? What does it mean if two strings are equal? Clearly not that their addresses are equal in memory, because that's a low-level implementation detail. All the characters are the same. So let me propose and let me introduce in version 1 of compare.c here. So compare1.c. Let me propose that we still get a pointer called s and store in it the return value of getString. Let's do the same thing with t. So none of the code is different. I'm going to add a little more error checking now. So now that we're sort of peeling back this layer in CS50 of what a string actually is, we need to be more anal about making sure we don't abuse invalid values like null. So I'm just going to check. If s does not equal null and t does not equal null, that means we're OK. GetString did not screw up getting either of those strings. And you can perhaps guess now, what does strcmp presumably do? String compare. So if you've programmed in Java before, this is like the equals method in the string class. But for those of you who haven't programmed before, this is just a C function. It happens to come in a file called string.h. That's where it's declared. And string compare, I actually forget its usage, but never mind that. Recall that we can do man str compare. And this is going to bring up the Linux Programmer's Manual. And it's frankly a little cryptic, but I can see here that, yep, I have to include string.h. And it says here under description, the string compare function compares the two strings s1 and s2. And s1 and s2 are apparently the two arguments passed in. I don't really remember what const is, but now notice, and you may have seen this already when you've used the man pages if you have at all, that char star is just synonymous with string. So it compares the two strings, s1 and s2, and it returns an integer less than or equal to or greater than 0 if s1 is found, respectively, to be less than or match or be greater than s2. That's just a very complex way of saying that string compare returns 0 if two strings are intuitively identical, character for character for character. It returns a negative number if s alphabetically is supposed to come before t, or it returns a positive number if s is supposed to come after t alphabetically. So with this simple function, could you, for instance, sort a whole bunch of words? So in this new version, I'm going to go ahead and make compare1 /compare1. I'll type in hello in all lowercase. I'm going to type in hello in all lowercase again. and thankfully now it realizes I typed the same thing. Meanwhile, if I type in hello in lowercase and hello in uppercase and compare them, I typed different things, because not only are the addresses different, but we're comparing different characters again and again. Well, let's go and fix one other problem now. Let me open up version 1 of copy, which now redresses this issue as follows. And this one's going to look a little more complex, but if you think about what problem we need to solve, hopefully this will be clear in just a moment now. So this first line, char star t, in layman's terms, could someone propose what this line here means? Char star t. What is that doing? Good. Create a pointer to some spot in memory. And let me refine it a little bit. Declare a variable that will store the address of some char in memories, just to be a little more proper. OK, so now on the right-hand side, I've never seen one of these functions before, malloc. But what might that mean? Allocation of memory, memory allocation. So it turns out, up until now, we haven't really had a powerful way of asking the operating system, give me some memory. Rather, we now have a function called malloc that does exactly that. Even though this is a bit of a distraction right now, notice that in between the two parentheses is just going to be a number. Where I've typed in question marks can be a number, and that number means give me 10 bytes, give me 20 bytes, give me 100 bytes, and malloc will do its best to ask the operating system, Linux in this case, hey, are there 100 bytes of RAM available? If so, return those bytes to me by returning the address of which of those bytes, perhaps? The very first one. So here too, and this is predominant in C, anytime you're dealing with addresses, you're almost always dealing with the first such address, no matter how big a chunk of memory you are being handed back, so to speak. So let's dive in here. I am trying to allocate how many bytes exactly? Well, string length of S, let's do a concrete example. If S is hello, H-E-L-L-O, what's the string length of S, obviously? So it's 5, but I'm doing a +1 on that. Why? Why do I want 6 bytes instead of 5? The null character. I don't want to leave off this special null character, because if I make a copy of hello and just do H-E-L-L-O, but I don't put that special character, the computer might not have, by chance, a \0 there for me. And so if I'm trying to figure out the length of the copy, I might think that it's 20 characters long or 1,000,000 characters long if I just never happen to hit a \0. So we need 6 bytes to store H-E-L-L-O \0. And then this is just to be super anal. I suppose that I forget what the size of a char is. We keep saying it's 1 byte, and it usually is. In theory, it could be something different on a different Mac or a different PC. So it turns out there's this operator called sizeof that if you pass it the name of a data type, like char or int or float, it will tell you dynamically how many bytes a char takes up on this particular computer. So this is effectively just like saying ×1 or times nothing at all, but I'm doing it just to be super anal, that just in case a char differs on your computer versus mine, this way the math is always going to check out. Lastly, down here, I check for null, which is always good practice. Again, anytime we're dealing with pointers, if malloc wasn't able to give me 6 bytes, which is unlikely, but just in case, return 1 immediately. And now go ahead and copy the string as follows. And this is familiar syntax, albeit in a different role. I'm going to go ahead and get the string length of S and store it in N. I'm then going to iterate from I equals 0 up to and including n, greater than or equal to, so that on each iteration I put the ith character of S in the ith character of T. So what's really going on underneath the hood here? Well, if this, for instance, is S, and I have typed in the word H-E-L-L-O, and there's a \0, and again, this is S pointing here, and here now is T, and this is pointing now to a copy of memory, right? Malloc has given me a whole chunk of memory. I don't know initially what's in any of these locations, so I'm going to think of these as a whole bunch of question marks. But as soon as I start looping from 0 on up through the length of S, T bracket 0 and T bracket 1, and I'll put this now on the overhead, T bracket 0 and S bracket 0 mean that I am going to be copying iteratively H in here, E, L, L, O, plus, because I did the +1, \0. So now in the case of compare1.c, in the end, if I print out the capitalization of t, we should see that s is unchanged. Let me go ahead now and do this. So make copy1 / copy1. I'm going to type in hello, enter, and now notice only the copy has been capitalized because I truly have 2 chunks of memory. Unfortunately, you can do some pretty bad and pretty dangerous things here. Let me pull up an example here now that gives us an example of a few different lines. So just intuitively here, the first line of code, int star x, is declaring a variable called x, and what's the data type of that variable? And what's the data type of that variable? That was not the cliffhanger. The data type is int star, so what does that mean? X will store the address of an int, simple as that. Y is going to store the address of an int. What is the third line of code doing there? It's allocating how many bytes, most likely? 4, because if the size of an int is generally 4, malloc of 4 gives me back the address of a chunk of memory, the first of whose bytes is stored now in x. Now, we're moving a little quickly. Star x means what? It means go to that address and put what number there? Put the number 42 there. Star y means go to what's at y and put the number 13 there. But wait a minute. What is in y at the moment? What address is y storing? Like, we don't know, right? We have never once used the assignment operator involving y. So y, as declared on the second line of code, is just some garbage value, a big question mark, so to speak. It can be pointing randomly to anything in memory, which is generally bad. So as soon as we hit that line there, star y equals 13, something bad, something very bad, is about to happen to Binky. So, I know. So let's see what Binky is going to end up, what's going to end up happening to Binky here in this minute
Binky,
or so look.
Wake up. It's time for pointer fun.
What's that? Learn about pointers? Oh, goody!
Well, to get started, I guess we're going to need a couple pointers.
Okay, this code allocates 2 pointers which can point to integers.
Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything.
That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step.
Oh, right. I knew that. The pointees are separate. So, how do you allocate a pointee?
Okay, well, this code allocates a new integer pointee, and this part sets x to point to it.
Hey, that looks better. So make it do something.
Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing.
Your magic wand of dereferencing? That's great.
This is what the code looks like. I'll just set up the number and...
Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y.
Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Oh!
Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it.
Good point.
Yeah, we allocated the pointer y, but we never set it to point to a pointee.
Very observant.
Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x?
Sure, I'll use my magic wand of pointer assignment.
Is that going to be a problem like before?
No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another.
Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over.
Okay, here goes.
Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13.
Yeah, sharing, whatever. So are we going to switch places now?
Oh, look, we're out of time.
But...
Just remember the 3 pointer rules. Number 1, the basic structure is that you have a pointer, and it points over to a pointee. But the pointer and pointee are separate, and the common error is to set up a pointer, but to forget to give it a pointee. Number 2, pointer dereferencing starts at the pointer and follows its arrow over to access its pointee. As we all know, this only works if there is a pointee, which kind of gets back to rule number 1. Number 3, pointer assignment takes one pointer and changes it to point to the same pointee as another pointer. So after the assignment, the 2 pointers will point to the same pointee. Sometimes that's called sharing. And that's all there is to it, really. Bye-bye now.
More on pointers, more on Binky next week. We'll see you on Monday.